Hello. In this video, we're going to derive the threshold capillary pressures for two important displacement processes. So we're going to start with the Young-Laplace equation. You can see written up here that the capillary pressure is the interfacial tension times the curvature, which is 1 over the two principal radii of curvature. And we're going to consider two displacements. One is what's called piston-like displacement. So the classic would be oil displacing water in a circular capillary tube. So it's got a circular cross-section of radius r, and then the non-wetting phase is displacing the wetting phase. You have basically a hemispherical meniscus, so it has the same curvature in two directions, but there's a contact angle here, theta. The capillary pressure, because R1 equals R2, which we're just going to call R, is 2 sigma over R. But what we need to find is the relationship between little r and big R. So that's the first example. The second example now is an example we would see, for instance, in imbibition. So it's the opposite process. So this is a non-wetting phase, say oil displacing water. Here we have a wetting phase, say water, in the corners of the pore space, displacing oil in the center. So here we imagine a tube that has a square cross-section coming out of the board. There's water in the corners. The water swells in the corners, moves out and moves out and moves out. The critical point at which any further increase in water volume actually leads to a decrease in the radius of curvature and a spontaneous snap-off event, filling the center of the pore space and potentially trapping oil elsewhere. Okay, this is a snap-off process. The critical moment is shown here. R now is the inscribed radius of this circle, which is actually, sorry, the inscribed radius of the square, which is half the length of the square. So capital R is this. Little r is the radius of curvature of the interface. And again, we have a contact angle theta. In this case, one radius of curvature is my little r, that's R1. R2 out of the plane of the board, we assume it's a straight tube. There is no second curvature. So this is infinite. PC is just sigma over r. But again, we need to find the relationship between little r and big R. That's the physics. The rest is basically geometry, relatively simple geometry. The difficulty thing is you have to do the geometry and understand the physics at the same time. And that's what causes the confusion. So the first thing to understand this derivation is you have to, yes, you have to draw the pictures yourself. You can stare at this video, you can go through something written down. Until you draw your own picture, you will never be able to do the derivation. So I've drawn it on the board. I'm going to draw it again on the whiteboard and go through it. And that's the point. It's drawing the pictures is basically the whole struggle. So what I'm going to do now is go onto the whiteboard. Okay, so here we have the whiteboard. What I'm going to do is do that first example, right? The piston-like advance. Okay, so I've got my pen here. Okay, there's supposed to be a straight line, not a very good straight line, but I do it nice and big. Okay, here's my meniscus. Okay, like that. Okay, I have a radius of curvature, right, which is R. Okay, and we have a contact angle here, which is theta. This is 90 degrees. This is my big R, okay, my capital R, and this is the solid here. Okay, okay, so now let's just write down the equation. PC is 2 sigma over little r, and I want a relationship between little r and big R. Okay, that's shown here. Well, it's all to do with triangles. Okay, it's geometry. So here's a right angle here. Okay, because this is just the radius of this cylindrical tube. So you can imagine in cross section, it's it's a circular cylinder, okay? Okay, this is my big R. This is the radius of curvature of the meniscus. Not drawn very well, but that's the point. You have to do the drawing yourself, not agonize about how well I do it. It's not about whether or not I understand it. It's about whether or not you understand it. Okay, so let's look at this. This is theta. This is 90. So this angle here must be pi over 2, 90 degrees, minus theta. So they all add up to 180. So this angle here, right, if this all adds up to 180, this must be theta. Okay, so now we've got a right angle triangle, okay? And now what we can write, okay, we've got a right angle triangle. This is the hypotenuse, okay? This is the adjacent to theta. We can write that cos theta is big R over little r. Therefore, 1 over little r is cos theta over r. So the capillary pressure for piston-like advance is 2 sigma cosine theta over r. So this is piston-like. And it's called piston-like because it's like a piston, you know, it's going in, out, in, out. Okay, it's piston-like advance. The capillary pressure, and this is the important thing, right, in terms of, you know, what we've got here, the capillary pressure is inversely proportional to the radius, the size. So capillary pressure is always inversely proportional to the size of the pores, okay? You've got an interfacial tension, that's obvious. You've got a factor of 2 because there's curvatures in both orthogonal directions. That's important. And then cos theta is basically the wettability term. Okay, so that's the first example that we've got on the board. Now let's do the second example, the snap-off example. So what we're going to do is we're going to erase everything here, okay? And we're going to take the second example. And again, you know, draw a picture, take your time. Okay, so this second example, right, we need my pen. Yeah, here we are. So the second example is going to be snap off in something of square cross section. Okay, so here is my square. Okay, here half of the side is R, and I'm just going to draw one of the menisci. Okay, all of the menisci were drawn. Okay, that's going to be this length here. Okay, and then here I have to draw it quite carefully. It's going to have a larger radius of curvature here. This radius of curvature I can draw down to here. Okay, that's going to be my little r. Okay, and I can also draw to here. That is also going to be little r because this is part of a circle. Okay, I can also define the contact angle here is now through the water phase, which is in the corner. That's theta, and this is a right angle. And then PC, we said this, there's only one radius curvature because out of the plane, we assume that curvature is 0. So PC is sigma over little r, and we want the relationship again between little r and big R. Okay, so how do we go about that? What we can do is choose another color, maybe blue, because of course we got water here in the corners. Okay, so we can draw a triangle. We can call this O, we can call this A, we can call this B. Okay, so I got the triangle OAB. One side is R, the other side is little r plus something, and OA is big R. Now let's look at the angles in this triangle. Here, just by symmetry, it's cut this right angle of the square into 2. So this angle is pi over 4, right? Not pi over 2, pi over 4. Okay, this is pi over 2, this is theta. So if we look at this angle here, then we've got to have pi, which is total angles of the triangle minus what else we got? Pi over 2 minus theta minus pi over 4. So this is going to be pi over 4 minus theta. Okay. Then you have to dig out your geometry at this point. There's the sine rule, which says, okay, this length divided by the sine of this angle is this length divided by the sine of that angle. So little r, which is what we want, divided by sine pi over 4 is equal to big R over sine pi over 4 minus theta. Okay, so we want 1 over little r, because it goes in that equation. Let's have a look where we are. So that's 1 over big R sine pi over 4, and then just multiply that out, right? And we got, okay, so this is going to be sine pi over 4 cos theta minus cos pi over 4 sine theta. Okay, so what do we get there? Let's have a look at that. Well, in this particular case, sine, so this is going to cancel out here, but because it's pi over 4, 45 degrees, the sine and cosine are actually the same. Okay, that's a bit of a trick here. So that's all going to cancel out. So we can actually write 1 over r, right? Let's write it out here where you've got a bit more space. 1 over r is 1 over big R, and then you've got cos theta, because it's got this term, 1 minus tan theta. Okay, so PC, okay, can be written as sigma over r cos theta 1 minus tan theta. Okay, so what are the terms of interest there? So let's highlight it maybe in yellow. Okay, again, we got the interfacial tension. It's inversely proportional to radius, right? The sort of size of the pore. That doesn't, that's nothing. You've got the cos theta term, okay? But you've only got one sigma. You've only got one radius of curvature. So before with piston-like advance, you had 2 radii of curvature. So it's always more favorable to do piston-like advance because you're curved in 2 ways rather than just one. That's the first point. The second thing is you've also got this contact angle to define term. And in fact, here you have to have a contact angle of less than 45 degrees. Otherwise, you can't have the water in the corners. Okay, so in fact, there's another constraint that says you've actually got to have quite a wetting phase. Here's the water in here and the water's moving out. You've actually got to have really a very strongly wetting phase for snap off to be favorable. And it depends on the angularity of the corners, of course, but you've got this 1 minus tan theta term. So this, if we're looking at snap off and piston-like advance, and the competition between the two governs, for instance, the pattern of displacement and imbibition, if it's piston-like advance, you've got 2 radii of curvature and just the cos theta. If it's snap off, 1 radii of curvature, so it's half for the same radius, and you've got this other contact angle term, right? And it's a minus. So what this means is that snap off is only favored when you can't do piston-like advance, or you go into a very narrow region of the pore space, as opposed to piston-like advance that you tend to see from a connected front, but then it gets impeded. Piston-like has to be connected, so it gets impeded by a wide region. So you're competing between basically piston-like advance in the wide region, the pores, against snap-off in the throats. Okay, so hopefully that's helped revise your geometry. Hopefully now you can see what the expressions are. I'm not going to write them down again. You can do this in principle for any system. So you know the geometry, you know the contact angles, you find the largest radius of curvature, so the smallest curvature value necessary for the meniscus to move through the geometry. That gives you the threshold capillary pressure. And I've done it for 2 simple examples, but they're 2 simple but very illustrative examples. Obviously, real porous media are more complex, but the basic principles are the same. It's inversely proportional to some indication of size, and there is a contact angle dependence, and there tends to be a factor of 2 if it's piston-like, and a factor of only 1 if it's snap-off. Okay, thank you very much.